What's up, guys? We're going to be going through some of the stuff with angled projectiles and mainly like the vectors that we can always draw on these types of paths. So it's going to be a very qualitative lesson, meaning there's not going to be really a whole lot of numbers at all. It's going to be really conceptual. And so it's one of those things that we can apply to like any situation for a projectile. I thought somebody was here. Waiting for a new person to show up. All right, let's get going. All right, so rules of projectiles, things that we've already kind of gotten hammered into our brain, but for horizontal motion, right, first off, let's get down here. And for horizontal, we have a couple important things. We know that the acceleration in the x direction is always 0, which tells me that the x velocity is constant. Okay, so that's stuff mainly for the horizontal direction. In the vertical direction, we know that the acceleration in the y direction is the thing that's always constant. Okay, and on Earth, we know what that number is for the acceleration. It's negative 9.8. If you go to different planets, that number changes, but remember the idea is the same. Like we know the acceleration just stays the same for anything falling in the air, whether it's on a different planet. And that's about it. Okay. So let's go ahead and draw this. Let's say, let's do the velocity vectors first. All right. So let's say you have a ball. And this ball gets thrown up in the air. It's launched at an angle and it comes back down. So it's a projectile. So it's going to follow a parabolic path. And at a couple points along this thing's path, let's say like, I'll just make this super thick. Let's say like right here, like halfway up. Actually, I'm going to put it like right there. At the top. Right? And then those same spots coming back down. We got there and what is it? Like right there. Okay? When we are drawing this stuff, I'm going to make sure this isn't thick boy anymore. I want to put the different velocity vectors on here. So first I'll put the horizontal velocity. So the horizontal velocity represents how fast the object's moving in the horizontal direction. So this ball is moving to the right. So I would put a vector on here going to the right, and I would call that horizontal velocity. Okay. Now, because all of our horizontal velocities are constant, that means that every single velocity vector from here on out I draw horizontally should look identical to that one. Should be the same magnitude, should be the same direction. Okay. So all I'm going to do is try to draw that the exact same. And if it's not the exact same, I apologize, but in spirit, all of these arrows are the exact same length. Okay? So everything has a constant horizontal velocity throughout its path. Now, if we look in the vertical, we know that there's always a y acceleration. And really one of the things I forgot to put is the vertical velocity. Oh my God, thick boy. Vertical velocity is always decreasing. Remember, we say decreasing because we know that the vertical velocity is always getting more and more negative. It's going down. Okay? So remember, the velocity vectors represent the motion. So when this ball is first going up, it has a upward positive y velocity. And when you first throw a ball up, it's going up real fast. That's a real big arrow, right? But that's the y velocity. About halfway, this ball on its way up is slowing down. It's going slower and slower because the velocity in the y direction is always decreasing. So the way we show that is we draw a shorter arrow. Okay, this one I made 1, 2, 3, 4 blocks long. This is 2 blocks long. And then at the top, at the very tippity top of its path, it has to stop for an instant before coming back down and changing direction. So there is no vector to put at the top in the y direction because the y velocity is 0 at the top at that one point in time. Now, as it's coming back down, because parabolas are beautifully symmetrical, right? This thing, if I had this case, I had two little blocks here going up. So if it's on the same exact spot on the other side of the parabola, there should be two blocks. But now my object is falling. So now my vertical velocity is going down. It's negative. And then here I got going straight down. Let's see, 1, 2, 3. I think that's right. Should be the exact same as our arrow over here, just pointing a different direction. Okay. Now, one of the things that will show up in questions is it's going to ask about overall speed as well. And if we want to think about the overall speed, because these are just vectors, components, right? These are just vector components. They only show how fast something is moving to the right or up and down, right? If we wanted to know, like if we put a radar gun like the cops use to measure speed on your car, right? Or like how they measure pitches at a baseball game, stuff like that. If we wanted to measure that, it's really a combination of these two vectors. So I'm going to scroll over to the side real quick to do a little side work. Okay, if I have something going to the right and I have something going up, and I want to add these two vectors together. Remember, I'm going to use what's called the tip to tail method. And I'm going to put, doesn't matter which one, right? You can always add stuff in any order that you want. But I'm going to put the tail of one vector against the tip of the previous vector. So the tail of the Vy went to the tip of the Vx. Okay? And if I wanted to find the result of this, what we would call the resultant vector, I go from where the tail of my first vector is, and I draw a new arrow to the tip of whatever my last vector is. Okay, so this is the overall velocity here. We call that vector v. Okay, and you can get a good idea of this. PhET has really good vector simulations. If we do this, right, this would be like originally what we had. These, I got a vector going to the right. I got a vector going to up, and I would put it tip to tail. And if I want to see what the vector sum is of these two together, right, there it is. If I make any of these vectors smaller, then it reduces the overall size of that sum. And you can even see this if I put the values on it. They're going to be random values, but you'll see this sum right now is 15.6. If I make the y velocity smaller, you can see that right here, this number is decreasing as I make it smaller. Right? If I make one of these bigger, then that number gets bigger. Uh-oh. There we go. Right? This number got bigger because I made the x component here bigger. So as we go through and draw, right, that vertical, that overall velocity would look like this. Right? Here, it's going to be, this y velocity is a little bit shorter. So like we said last time, it's going to be a it's a smaller overall velocity along with a shallower angle. Here it'd be the exact same as whatever the x velocity is. Here again, we combine two arrows going down, right? So if I take this arrow and make it going down, well, now my sum is going downward. Okay, so same idea. Same idea. Now this one would be longer and steeper. Okay, so those are all our velocity vectors. let's say I take this same thing, but I want to talk about acceleration. So we have our ball, goes up, comes down. I got a few points along the way that I want to take a look at. And I want to know at these different points, what is the acceleration vector doing? Well, the acceleration vector, let's get crazy. Let's use rainbow color, right? There's a couple things that I know from my rules. I know the acceleration in the x direction is always 0. And I know the acceleration in the y direction is always constant for any projectile, okay? So if I want to apply those rules and have them show up here visually, in the x direction, if this is 0, then I have no arrow to draw anywhere, right? That would be like an arrow with a length of 0, so it's just not there. So there's no horizontal vectors to draw. Vertically, I have an arrow going down. That is the acceleration in the y direction. This would be how much its velocity is changing by every time. And if it is constant, that means it never changes. So it's going to stay the exact same every single time, meaning the magnitude is always going to be the exact same. So all of those hopefully look like identical arrows, but there's no no horizontal acceleration vectors to draw because it's 0. And all of the vertical acceleration vectors should be the exact same. They are constant. Okay, so this is how we show our vectors for all the different types of velocity, for the components and the overall, and for the accelerations. Okay, when you are being asked about problems where there's a object flying through the air, and talk about what at point P, what is its horizontal velocity doing? Horizontal velocity, no matter where you're at on this path, all looks the exact same. So we could say that it's never changing, right? It never changes, no matter where you're at. Horizontal velocity never changes, okay? Vertical velocity, a little different, but then just go back and think about how we reasoned through all of our different velocity vectors, okay? All right, let me know if you need something a little more with the velocity vectors, and otherwise, have a good day.